We saw in the last video that type 1 and type 2 errors have all sorts of applications into screening tests in particular. So screening tests for security tests for your computers and phones, and we focused a little bit on medicine. So the type 1 error is a false positive. Sorry, I forgot to fill out that blank before. And the type 2 error is a false negative. And both of these are pretty dire. In medicine, the false negative is particularly dire for reasons that were explained right here. So you can imagine that something that has this many applications and has its tentacles into this many real life problems must have its own field of study and a lot of applications and definitions surrounding it. And there are. Now, we're not going to get into all of them, but we want to touch on two of the most important definitions, which are the sensitivity and specificity of a test. And these are just some of the many definitions that could be wrapped up into making decisions and hypothesis tests. Now, sensitivity is called the power of a test, or it's the true positive rate. It's the probability of correctly rejecting a false positive. Now, in a screening test, what that means is it's going to be the proportion of actual positives which are classified as such. All right, so let's look down here to try to get a better sense of this. So I have a screening hypothesis test here. And I'm just noting that the null and alternative would be that you do not have the trait as the null, right? We assume everything's fine. We assume you don't have the disease or that the computer doesn't have a virus or whatever. The alternative is that you do have that trait. All right, now if that's the case and the actual situation here is H0 is true, that means they truly do not have the trait or the computer truly does not have the virus or whatever. If H0 is false, that means that H1 is actually true, and that means that they truly do have the trait. Now keep in mind, actual reality situation we don't really get to know, but we're just keeping this in mind for a philosophical discussion. Now, over here we have our tests, our decisions. So if we do not reject the null, that means you're testing negative. And I don't just mean this for medicine. I could mean it for a computer virus for your phone or something like that, for your screening software for your phone. And then if it's rejecting the null, that means that it's testing positive, and you get the little warning on your phone going, this is going to be bad, this is a virus, that kind of thing. All right, now sensitivity is the power of the test. It's down here. It's the probability that you're actually going to make the correct decision over in this corner. So the probability of correctly rejecting a false null hypothesis. So you're rejecting the null and the null is false. It's the chances of you doing that. Now you'll notice here that I give you a formula for it, and it's 1 minus beta. Because beta is the probability of making this type 2 error, 1 minus beta is the power of that test, also known as the sensitivity. Now you'll notice that means that these two columns here, these two cells here, must add up to 100%, and they do, right? So if beta is 0.01, then power is 0.99, right? The sensitivity is 0.99. Similarly, the specificity, let's look over here. Specificity is the probability of correctly not rejecting a true null hypothesis. So in screening tests, it measures the proportion of actual negatives that are going to be classified as such. So you can see it right here. It's this correct corner over here. And in confidence intervals, that has to deal with your confidence. But for a hypothesis test, it's 1 minus alpha. It's your specificity. So they truly don't have the disease, truly do not have the disease, and they test negative. So that would be 1 minus alpha. And then alpha is the probability of that false positive. And again, these two cells must add up to 100%. So I kind of put a little note right there. Note that the two columns, must add up to 100%. So alpha and 1 minus alpha and beta 1 minus beta. And this is a little bit different than just a regular two-way table. So these probabilities in here, that's because these probabilities are based from section 5.4, which is conditional probability. So there's a little bit more going on in the background here probability-wise, but suffice it to say that these two cells must make 100% and these two cells make 100%. So of all the people that don't have the trait, they must test into these two groups, and all the people that do have the trait must test into these two groups. All right, well, this is kind of esoteric, right? There's a lot going on and there's a lot of definitions. So let's think about the medical screening thing again, just to kind of put ourselves in this context. So the medical screening would be that the null hypothesis, the person does not have the disease, and if the sensitivity is the probability that they will test positive if the person has the disease. So they're in this column, sensitivity. They're in this column over here. They truly have the disease and they're testing positive for it, right? It's the probability of testing positive given that they're over here in this column. Specificity over here is the probability that they test negative given that they're over here. They truly don't have the disease. What's the chances they're going to test negative? And that is the specificity. All right, now let's think about this for just a second. If you have a test that has high sensitivity, right? The people that truly do have the disease are going to test positive, which is a good thing in medicine. Actually, in medicine, most tests are usually highly sensitive. What that means is that your beta will have to be very, very low, right? So if you have a high sensitivity, your beta will be low because they're complements of each other, right? So a very, very low beta means that, if your test result is negative, you can be nearly certain, but not 100% certain, of course, because we're never 100% sure, but nearly sure that the person truly does not have the disease. In other words, a highly sensitive test helps rule out disease, right? Helps you know which people in your population truly do not have it. So let me say that one more time. If your sensitivity is high, that means that your beta is low because they add up to 100%. If your beta is low, you're not going to get a lot of false negatives. And what that means is when people get negative on their test, you can trust it, more or less, right? Still not 100% sure, but it's pretty sure. And just for the record, medicine tends to err on the side of high sensitivity because they really don't want false negatives. Not so true maybe for other types of screening tests, but definitely true in medicine. Now, specificity was the probability of testing negative right here if the person truly does not have the disease. Okay, now think about this. If you have a high specificity, what that means is that your alpha is going to be very low because they have to add up to 100%. So if you have a high specificity rate, that means you're at a very low alpha. And that means that if your test result comes out positive, you're pretty sure, but not 100% sure, but you're pretty sure that the person truly does have the disease. So a specific test helps us know that we really do have that disease with a high confidence level. Okay, now we can't have both. The problem is that if you try to make it so that you're super, super sensitive, you often are meaning it that you super, super sensitive means a very low alpha, but a very low alpha will mean that you have kind of a higher, super sensitive test means a very low beta. Apologize. And a very low beta means you have a high alpha because they're on kind of a teeter-totter together, right? So you lower your beta, you raise your alpha ish, right? There's more going on, but that relationship is there. And what that's going to mean is that your specificity is going to go down, right? So there's a relationship, just like there was between alpha and beta. As a matter of fact, quite frankly, because of the relationship between alpha and beta. Because if alpha goes up, beta goes down, and vice versa. That's going to mean that if I lower my sensitivity, or raise my sensitivity in medicine, we always want to raise it. So if you raise up that sensitivity, beta will go down. If beta goes down, alpha goes up, and then your specificity goes down, right? And so there's this relationship going on. So I just typed that up. So sensitivity and specificity are on a seesaw together for a lot of reasons, and one of them is that because alpha and beta are tied to these two things. So if you raise your sensitivity in a medical test, you're going to lower your specificity, and that's a trade-off, right? So it depends what matters more to you, sensitivity or specificity. What matters more, making a type 1 or a type 2 error? In medicine, they tend to err on the side of high sensitivity, so lower betas, therefore higher alphas. and lower confidence, right? That's just how it works in medicine. In other kinds of tests, it might be the opposite. If you really want to make it so you don't do type 1 errors, then you're going to lower your alpha really low. That means that your beta is going to go higher, and so will your specificity, but then your sensitivity will go lower, right? So there's trade-offs that you have to make between sensitivity and specificity, just like alpha and beta. All right, so I just put a little note up here, which is that in medicine, sensitivity is usually high. So that way that beta can be low, and that way we can keep the probability of a type 1 and type 2 errors low. Or excuse me, probability of type 2 errors, because type 2 errors are bad, 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 right? But different application fields like I don't know, computer screening or something like that, or maybe when you're working on a conveyor belt, you might have different reasons for choosing higher specificity for some reason and lower sensitivity. So it just depends on your context.